Hi, everyone. So my name is Maximilian Rimberkus, and it's my pleasure to actually introduce today's speaker for the QuTech360 Seminar from today. It's Jiwon Yun. And Jiwon Yun is a postdoc in Tim's group, and with the research focus on characterizing quantum gates and spins for spins in solid states. He did his PhD in Seoul National University in South Korea, studying the interaction between an NV center and its environment. He focused both on the interaction between the NV center and the carbon nuclear spins and the action between the NV center and its thermal environment. After that, he moved to TU Delft as a postdoc. And here his research focus is what you also see today. It's on characterizing quantum gates applied to NV centers in this system. And before I give the stage to her, a quick announcement is, if someone from the online audience is having questions also during the talk, please just write them in the chat. We will answer them afterwards. And if questions from the audience arise, there's time after the talk. And with this, the stage is yours.
Thank you, Max, for the nice introduction. And thank you all for joining this QuTech360 talk. I'm Jiwon Yun from Taminiau Group. And today I'm very excited to share my talk regarding high-fidelity gates for spin qubits in diamond. So this work was done with many of my colleagues, brilliant colleagues, Hans, Kai, Marty, Luke, and Benjamin. And today we want to share some of the recent results we got from this research, which was very exciting. So let's dig in. So first, as a motivation, I want to kind of say that these days in the science and technology field, a lot of people are starting to gain interest of quantum phenomena. And there are also attempts to use these quantum phenomena for computation or communication or internet or things like that. Especially here in QuTech, in our quantum internet division, we are trying to demonstrate quantum internet or distributed quantum computation using these quantum technologies. But if we look behind these quantum applications, we can see that, especially if the application is regarding quantum information, we can see that they are actually having these diagrams behind them, which are called quantum circuits. And in these quantum circuits, you can see these boxes, which are called quantum gates. So most of these applications are all built up with these units called quantum gates. So what are quantum gates? In a quantum computer or a quantum device, everything is based on a bit, a quantum bit, or in short, a qubit, which is a two-level system, which you can describe as an arrow on a sphere or so-called blosphere. What a quantum gate does is it changes a certain arrow, an initial state, to a different direction, which is the final state. So a quantum gate is just a map that maps your initial arrow to your final arrow. So your initial state to your final state. And today I want to explain this quantum gate using a scheme of a vending machine. So I hope a lot of you guys are familiar with this concept of a vending machine, which can provide you chocolate when you're very hungry, of course. So what does a vending machine do? You go in front of a vending machine and you can see a display. There are numbers that correspond to chocolates. And then if you find the chocolate you want, in my case, I like Twix. I find Twix and it's over a number 26. What do? I go to the dialing pad, I dial in 26, and then the vending machine gives a Twix for me. And then I can eat it, of course. So this vending machine is kind of a map that maps a number to a chocolate, which is kind of what a gate does in the quantum world. So if you stand in front of a vending machine, especially the one that is on the first floor of this building, you can see that this kind of display. So you see 26, on top of it, there's a Twix, 27, on top of it, there's a Snickers, and 28, you have a Bueno. What does this mean? If you go to the dialing pad, you press 26, you'll get a Twix out of your vending machine. Of course, you have to pay, but then you'll get a Twix. If you press 27 and pay, you'll get a Snickers. And if you press 28 and then pay, you'll get a Bueno. So this is your map of your vending machine. So now what is a quantum gate? For example, I'll try to describe a gate of a Rx 90 degrees gate, which means that it's gonna rotate your whole block sphere around the x-axis by 90 degrees. What does this do? It will rotate your y state to a plus z state. It will rotate your z state to a minus y state, and it will rotate your x state on its own place. So it will go back to x. So you can think of it as the display on the left here. So if you press X, you'll get an X. If you press Y, you will get a Z. And if you press a Z, you'll get a minus Y. So this is kind of the display of your quantum gate. Of course, in the quantum world, the input and output are not as discrete as vending machines. So you need actually a little bit more information to describe the whole gate. So now what we actually need is this kind of box, a 4x4 box. And this will now describe the whole process of your gate. So, but for the most characteristic cases, you can actually compare it to the display on the left, since the topmost row means your input state and the leftmost column means the output state. So if you input, and the red means +1, the blue means -1. So if you input a X state, you'll get a plus X state. And if you input a Z state, you'll get a -Y state, and so on. So this is kind of a little bit more information version of this display you see on the left. So this is the display of your vending machine or your quantum gate. And this is what people call process matrix. So once you have the process matrix of your gate, you can actually know and predict what your gate will do to any arbitrary quantum state you have in your system. So it's very important to know the process matrix of your gate. Okay, so now we know what the gate does. And then the next question will be, or we know what the vending machine does, and then this kind of question can pop up. So I'm very hungry now and I want to go and buy a chocolate on, let's say, the vending machine on this first floor. But I'm actually curious how reliable this vending machine is. Like, I really need the chocolate, I want to go and pay, but like, what is the probability to get the chocolate that I want? Because like, if this is like a very hard day and I really need a last push of sugar, but then I press 26, I pay, and then if nothing comes out, like somebody will get angry or frustrated. So in this sense, today, as the maintenance person of this vending machine, I want to kind of evaluate on average how well this vending machine will react. So on average, how well this vending machine will satisfy the customers. So to have like a single number to represent how good this vending machine is, what will you think of? Like, what will you try to think of to get a number to describe how good this vending machine is? In my case, what I will think is I will try going through all of the past orders I did on the vending machine. Like, okay, yesterday I ordered a Twix, the day before maybe Snickers, and then like in the past year, I think I did like 20 orders. And then among those orders, I will think how many times did I get the right order? Like, yeah, that I got the Twix, the Snickers, but at some point, I think I ordered something, but nothing came out and I got angry. So in the last 20 times, I got like one wrong, then that's like, okay, 5% infidelity. So let's say that a vending machine on the first floor has a 95% fidelity. So this is kind of what I will go through to explain what the fidelity of the vending machine of our first floor. So you go through all the possible inputs and then the outputs and see all the cases where you got it right, and then you average out how reliable it is. And then this concept is equally used in the quantum field, or relatively equally used in the quantum field, under the name average gate fidelity. Now it's a little bit more complicated because your output isn't as discrete as a vending machine. So you can't say yes or no for everything, but you have to actually get the overlap of your output state. So for every possible input state, you will get the output state and you will see what the state fidelity is of the output state. And if you average out all the state fidelity of the possible output states, that will give you a single number of the gate, which is your average gate fidelity. But in the easy sense, it just means how reliable your gate is, like how sure are you to get the right chocolate that you want. And this is the concept of average gate fidelity. So now, if we have a gate, we know that if we get the process matrix, we know the map to describe how our gate will work. And then if we know the average gate fidelity, we have a number to describe how reliable this gate is. Okay, so next is how do we measure these process matrices average gate fidelity? There are many ways that are suggested to do this, but in this work, we are going to focus on using a method called gate-set tomography. So this gate-set tomography in principle is similar as just testing how good a vending machine is. So what you do, there is a preparation fiducial, which is actually preparing the input state of your quantum gate or your vending machine. So for example, this is the numbers that you will put in your vending machine. And then there are the measurement fiducials, which is a way to measure out what your output state is. So in a sense, it's getting the chocolate out from the vending machine, tasting it and say, oh, this is a Twix. So you have your preparation fiducials, measurement fiducials, and these will in principle give you the information of your process, of the map of the display of the vending machine. But for some cases, the error might be small. So if you test everything only once, you won't be able to check it. Like if you press every number once on the vending machine, they were all perfect, then maybe you can say the vending machine has a 100% fidelity. But if you do it multiple times, then there are small errors in the system and then it will start suddenly pop up. So this germ in the middle is kind of there to amplify the small errors that might be in your gates. So you can try gates multiple times and amplify the error to actually measure the small errors within every gates you have. So these are the three features within gate-set tomography. And advantage of using this is all three features here are only made of gates that you want to characterize. So this is a little bit different from a method used before called process tomography, where you have to assume that your preparation and measurement is perfect. However, in the real quantum world, these also can have errors, which are called state preparation and measurement errors, or spam errors in short. In gate-set tomography, since you know that these preparation and measurements are also made of gates that you want to characterize, it considers that they are imperfect and it puts it into the process matrix. So it will give you a little bit more reliable process matrix that is a bit more robust to the spam errors of your system. So in this work, we use gate-set tomography to get the process matrices of our gates, which is just the display of the vending machine we want to characterize. So now to sum up the first part, to characterize a gate, we have to know the process matrix of the gate. To know how good your gate is, we would like to know the average gate fidelity of the gate. And finally, to get these measures, we will use gate-set tomography. Okay, so where do we want to apply this? So for me, I am interested in spin qubits in solid state, especially spins in the nitrogen vacancy defect in diamond. So how do we use these spins? We prepare a diamond in 4 Kelvin to optically adjust them resonantly. So what we do is, what you see here is a 4 Kelvin Montana cryostat. And in this Montana cryostat, we put in a printed circuit board, a PCB, which has a diamond in the middle. So if we zoom in, you can see that there's a diamond here. The middle is a diamond platelet. And on the surface of the platelet, we fabricate gold strip lines, which we use to make the gates to control the spin qubits. Since we are using spin qubits, once we drive them with resonant microwave or RF frequencies, they can directly translate into gates on the qubit itself. So all the gates go through these gold strip lines. And then if we zoom in a little bit more next to the strip line, there are these spherical lenses called solid immersion lenses, which we use to collect the photon coming out from these defects a bit more efficiently. And the picture on the right bottom, you can see there is a very bright spot in the middle, is our defect, our nitrogen vacancy center. And in the MV center, we have an electron spin and a nitrogen nuclear spin that we can use. And today we're going to focus on these two spins, the electron spin and the nitrogen nuclear spin of the MV center. So let's zoom into this two spin system. So first we have the electron spin and the nitrogen spin, which are coupled relatively strongly with 2 megahertz. And then, since we want to demonstrate how good the gates are to these two spins, we want to know what might bother the gates, what might be the noise source in this system. And mainly, since these are spins, every magnetic sources can be a noise to the system. And one main thing is that our nitrogen vacancy resides in diamond, and diamond is made of carbon. But natural diamonds, natural carbons, by 1.1% exist in their carbon-13 isotope, which has a nuclear spin. And since every spins can interact with each other, these can be noise sources. So in this work, we actually prepared a isotopically purified diamond. We reduced the density of this carbon-13 and enhanced the carbon-12 ratio so that now in our diamonds, only 0.01% of the carbons have a nuclear spin that can interact with our electron and nitrogen spin. So this kind of makes us a little bit more sure that we can say the electron spin and nitrogen spin that we use are very well isolated from the environment, and we can consider it as an isolated two-spin system. So this is the system we use, but more to that, we also figured out that in this diamond, there was a little bit more impurities than we expect, which was some other electron spins, some nitrogen impurities with electron spins dangling around it. We call them P1 centers, and the density of these P1 centers are known to be 75 ppb from previous results, and these we'll discuss a little bit later in details might be limiting our gates fidelities at the moment. So this is our system. In the system Hamiltonian, a little bit more can come in, such as the external magnetic field that can fluctuate, or some electronic noises that come in from the control that we do with electronics, and so forth and so on. So yes, this is our system. What gates do we prepare on this system? So first, for 2-qubit GST, we prepare 6 gates on this system. So first on the electron, we have an identity gate, which we make by applying 8 pi pulses on the electron. The pi pulses we design with a Hermite pi pulse, and then the amplitude we optimize to rotate the electron exactly or approximately exactly to 180 degrees. And then by applying 8 of the pi pulses, effectively, it's just an identity on the electron. And since it's an electron gate, it does nothing to the nitrogen. So this is what we call an identity gate in our 2-qubit GST. After that, we also prepare, yeah.
Why did you choose like 8 pi pulses?
So to be a little bit more into detail, we use this XY8 sequence, which has this XY, XY, YX, YX kind of pattern. And if you do this, this is a little bit more robust to the amplitude error and the detuning error for the pi pulses itself. So it makes this identity a bit more robust to your electronic controls. Yeah, so that's why we chose XY8. After that, we also prepare a pi/2 gate on our electrons, both for an X phase and a Y phase. And these we also prepare with a Hermite pi/2 pulse envelope that is sandwiched between also 2 XYAs so that the electron is always decoupled from the system. After the 3 electron gates, we also prepare a nitrogen nuclear spin gate, which we make with a dynamical decoupling radio frequency gates. This is in principle just driving the nitrogen with its resonance frequencies, which is 7.1 megahertz in this case. But we're driving the nitrogen with 7.1 megahertz, but at the same time, we want to also decouple the electron. So we cut this nitrogen pulse into pieces, and then we interleave it with also electron pi pulses in between. Because we flip the electron every time, we have to carefully calculate the phases of each of these RF blocks. But after we do that, we can make a very nice unconditional nitrogen rotation gate using this scheme. So with the right phase conditions, using this kind of gate sequence, we can prepare a X pi/2 gate and Y pi/2 gate on the nitrogen. And also, if we use a different phase condition where we flip the every even RF pulses by 180 degrees, then this could actually be a conditional gate where the nitrogen rotates plus pi/2 when the electron is in its 0 state and minus pi/2 when the electron is in its 1 state. So here we have a X and Y pi/2 gate on the electron, X and Y pi/2 gate on the nitrogen, and the 2-qubit gate, which is what we require to run a full 2-qubit gate set tomography on our system. So using these 6 gates, we ran a full 2-qubit GST analysis. And from the reports, we were able to get this huge process matrix, which represents how our gates actually act to the system. And from these process matrices, we were able to extract the average gate fidelity number, which tells us how good our gates are. And in our result, we were very excited to see that all of our gates that we used in this two-qubit system were exceeding 99.9% gate fidelity. Yes, so how good is this? So we also did some research in the field on what people report for their two-qubit gate fidelities. And this is what we got from the researchers from the past. There were many, many incredible and very exciting researches done in this field among various platforms. But among all of the reports, we can see that only a few of them were able to report a number over 99.9. So from this, we were very happy to see that our two-qubit gate fidelity was actually among the best gate fidelities in the field at the moment. Of course, this doesn't mean that, okay, Diamond is the best platform. You should make quantum computers out of Diamond. No, because this is a very well isolated two-qubit system. And then if we have to start discussing about scalability, then there's really nothing much to say at the moment regarding this. But regardlessly, we think that seeing this high number means that we very well understand what a very well isolated two-qubit two-spin system in a solid state can do. Like we understand the Hamiltonian, we understand what's happening, and we can also control this two-spin system very nicely using RFs and microwaves. So this is a very promising result for people who want to use spin qubits in solid state. So we were very happy about this result. And then we wanted to try to push this result a bit more. So this is for the full two-qubit space, but for certain conditions, we can also prepare one of the qubit in an eigenstate. And then for a single qubit gate, we might be able to push the numbers a bit further. So we try that. So for the electron gate case, if we prepare the nitrogen in an eigenstate, and then if we do a single qubit GST on the electron, we see that we can already boost the numbers up to like 99.99 or 99.98, which is already higher than what we see for two-qubit gate fidelities. And for the nitrogen case, this was actually quite amusing. But once we prepare the electron in an eigenstate, and if we start driving it directly with RF, we can see that the nitrogen single qubit gate fidelity can go up to 99.999, which is like 5 nines, which is very impressive. Like it will take forever to make that an error, but yes, so we see that these spins in solid states are very stable, very well controllable, and are promising to be used as qubits using RF and microwave control. Okay, so this is about the control of the spins. Now we want to tune out a little bit and go back to the two-qubit process matrix result. So from the two-qubit GST result, we can get the full two-qubit process matrix of all of the gates we use here. And then, so what can we do with that? So we wanted to demonstrate how we can use this information, and we made kind of an example quantum circuit that we want to demonstrate, which is a swap demonstration. So in our nitrogen nuclear spin and electron spin two-qubit system, we wanted to see how good a swap gate is. And here to demonstrate a swap gate using only the characterized gate we characterize with GST, it actually requires 17 of these characterized gates. So the swap circuit is a circuit of 17 gates, and we tried to apply this many times on our system to see how the electron evolves during this process. And at the same time, we wanted to predict what the GST process matrix predicts by using the process matrix information with the same circuit structure. And the result is what you see on the left bottom. So the circular markers are our measurement results that we measure every time we apply even number of swap gates. And then the solid lines are the prediction from the process matrices we got from two-qubit GST. So what you can see here is that the process matrices actually represent the gates very nicely, and you can actually predict how your electron state will evolve quite nicely, even up to like 800 gates that you apply to your system. This means that the process matrix really explains your gates very well. And even on the nitrogen side, you can see that it tracks how the nitrogen evolves, at least trend-wise, quite nicely. So this kind of made us be even sure that this characterized process matrix is quite reliable. However, we also measured the average state fidelity of the after applying every swap gate, and we saw that the average state fidelity drops to 0.5 already at 20 number of swaps, or between 300 to 400 application of bare gates. So just before I told you that all of our 2-qubit gates had fidelities over 99.9%, but already after applying 300 to 400 gates, our swaps seem to have like completely lost this information. So there was a mismatch between what we expected from the gate fidelity number and what we actually measured. So where does this discrepancy come from? And from this, we now dig into where our errors are originating from. And this we can see from the error generator. So another advantage of having the full information of the process matrix is that you can actually also pinpoint where your errors are coming from. So in the process matrix space, it's a little bit difficult to directly see where your errors are coming from, but you can actually move into an error generator space, which is assuming that your measured process matrix is just a multiplication of the process matrix of your perfect gate, and then you have an error process matrix after it. And then what you do is you analyze what generator can produce that error process matrix, which is the boxes you see on the right. So once we go into this error generator space, we can see that we can easily divide which part of the error generator comes from coherent parts, so which comes from unitary errors in the system, and which part comes from stochastic errors, from probabilistic errors. So using these informations, we can first divide the origin of our infidelity. So per each gate, we have a certain infidelity. We can see which portion of the infidelity comes from a control error and which portion of the infidelity comes from a stochastic error. And at the moment, we see that most or a lot of the errors that we measure right now are actually coming from stochastic errors, but still some significant amount are coming from control errors of our gates. So I'm saying control error, stochastic error right now, but what do these really mean? So first, for control error, what control errors can be is that you, for example, you want to do a pi over 2 gate, a 90 degrees gate around the x-axis, but like these amplitudes are continuous. Like you can do a little slightly over rotation. You can rotate 91 degrees, you can rotate 98 degrees. If you do these over rotations and under rotations due to the limitation of your calibration process, then this can come in as a control error. Furthermore, what can come in as a control error? In your system, since like especially for our system, since the electron spin and nitrogen spin are always interacting with each other, we can always have some unintended rotation, unintended control to the qubits that we have. So for example, what we saw in our system explicitly was that when we used a specific tau for our XY8 and we just applied this XY8 to the system, actually the nitrogen was coherently rotating while we were only applying pulses on the electron. So this we think is coming from some unknown ZX hyperfine coupling between the electron and nitrogen. But for the specific 8.3 microsecond evolution time, we see that the nitrogen shows a clear oscillation pattern. However, we were able to pinpoint where this was originating from. And then we figured out that if we used a very smart tau on the left, 7.304 microsecond, that actually cancels out the rotation that happens on the nitrogen. And then we see that the nitrogen no longer rotates and shows a very flat line. So like using the information that what you have in your control error part, you can actually pinpoint the source of the error, and some of the unintended rotation you can actually also tackle and try to reduce it. And this was also one step we could take to increase our gate fidelities. So control errors are all unitary errors that has nothing to do with the decoherence of the qubit. But the second part of the error are stochastic errors. So what are stochastic errors? These are coming from like fluctuating B fields in the environment mostly, since we're using spin systems. And we can kind of divide the stochastic errors into two different classes. So one of them is a quasi-static noise. What are quasi-static noise? These are B field fluctuations that are relatively slow. So when you do a single run of measurement, the quasi-static noise can be assumed to be static. So it can be assumed to be constant. For example, where does these come from? These come from single spins in your environment. So for a single run, all of your spins in the environment in your spin box will have a certain a random configuration, but a fixed random configuration. So a single run, you have this kind of configuration. For your second run, you have a completely different configuration, but within that run, they will all be fixed to that certain configuration. Why is this important? If your noise is quasi-static, you can actually do a decoupling sequence to your spins, and then that will cancel out your noise quite nicely. This we will later show that show by simulation that if you have quasi-static noise, it will do very little. It will have very little effect to your gate fidelity once you put everything in decouplings. So the first class is quasi-static noise, and then we have dynamic noise. The dynamic noise are relatively fastly fluctuating noise in your system. Where can these come from? In the spin case, these usually comes from spin pair, where spins interact with each other and they can flip-flop with each other. So once they start flip-flopping with their interaction strengths, these are way more difficult to cancel out since they are fastly fluctuating. So these cannot be canceled out using a decoupling sequence. And this is what we consider now that are mainly limiting the infidelity that's coming from this stochastic error part. So to show you what I just mentioned, so we simulated our gates and applied a quasi-static noise to the system and saw how much it affects the gate fidelity. And for quasi-static noise, we can see that even up to a detuning, like if you have a quasi-static noise up to 1 megahertz, it still doesn't affect your gate fidelity that much. Like you still have over 99.98 fidelity for your electron gates. So it's very difficult to hurt the gate fidelity of your gates once your gates have embedded decoupling sequences within it. However, so then most of this stochastic error comes from the dynamic noise of the system. And we actually explicitly measure using the electron that while doing this XY decoupling, the electron feels dephasing, as you can see on the top right, on the right, like the right top, and also it can feel bit flip, as you can see on the right bottom. So this is what we think we see on the stochastic error generator as the YI and ZI term on the leftmost row, that we experience this dephasing and bit flip coming from the flip-flopping boss around our MV center, or maybe some 50 hertz electronic noise. So at the moment, the dynamic noise is what we consider to be most likely the source of infidelity for the stochastic error part. So now we divided our errors into control error and stochastic error. Why was this important? Now we will go back to the swap demonstration, where we saw that the fidelity after applying many numbers of swap were actually decaying faster than we expected. So how do we use this information? So why this can actually decay faster is because some coherent error, some control error can actually coherently build up while applying these swap gates. So if coherent error or control error coherently builds up, then it can decay faster than you expect from the average gate fidelity you see. So how can we actually check if it's coming from coherent or control errors? We actually first try to wrap all of our swap gates with Pauli twirling. What this does is you apply a random Pauli gate before and after the gate that you want to apply, which prevents your control error to add up. So it kind of mixes up your control errors so that they have a random direction every time. And once we do the Pauli twirling, as you can see in the purple and cyan curves on the right, you can see that the fidelity already goes up quite dramatically since the control error can no longer build up while applying this multi-number of swaps. However, this is one way to cancel out your control errors, but in our GST case, since we have the full information of the process matrix and we know what the control part of our error is, we can actually try to tackle this problem a bit more smarter. So what we do is we do another attempt where, since we know that this is coming from some control error, we actually interleave our swaps with 2 electron pi over 2 gates. So we do a swap gate and then 2 electron pi over 2 gates, swap gate, 2 electron pi over 2 gates. And by doing this, we get the green curve, which you can see for the small number of swaps, it can actually be even better than doing the Pauli twirling. So what this means is if you have information on what kind of control error you know, and if you find a way to tackle those errors, you can actually get a better performance on your quantum system, even by applying more gates. Like in principle, applying more gates, you might think that it will hurt your quantum circuit, but if you know your control error and if you know how to cancel them out, then you can actually win by applying more gates in this case. So I think this really shows how powerful it is to have the information of the process matrix, the whole process matrix, and then to decompose your errors into control part and stochastic part. So this, so this is showing how it bumps up. But now, so this was my talk. I want to wrap it up now. So what I wanted to deliver today was we were able to extract the full process matrix of our gates on the 2-qubit system using GST, and they were showing very good fidelities, over 99.9%, which tells us that we have very good controllability of this well-isolated two-spin system. And then also, if you have the full information of the process matrix, you can use it to predict how a quantum circuit will act on your quantum system. Furthermore, since from the full process matrix information, you can extract error generators. From the error generators, you can actually try to pinpoint what the source of your infidelity is for your quantum gates. And finally, if you know the information of your control error generator, then you can try use the information to actually design a quantum circuit that is optimized to your specific quantum system that could show better performance and enhance the quantum control of your specific system. So yes, this work was done in Taminiau group with many of our brilliant and very happy colleagues. I was very happy to do a lot of exciting discussions with them. And thank you all for listening to this talk.
That was a wonderful talk. Are there any questions?
Yeah. Can you also do Hadamard gates?
Yeah, so like using these gates, we can build up a Hadamard gate if that's what you're asking. Yeah. So yeah, this is a universal gate set in that sense. Yeah.
Thank you.
Yeah. Okay.
Why when prepared in an eigenstate is your fidelity higher?
So in a sense, you can kind of control the interaction between the two spins. Like you're limiting the interaction to a certain interaction. And then you can kind of optimize to that certain condition. Whereas if the other spin is free, you have to consider every cases for the degree of freedom of the other spin. Yes.
I think I typed my question in the chat window already.
Yeah.
Well, anyhow, so my first question is about the swap experiment. So you did a long sequence with many swap gates, and my question is that how do you know if for example, if your last swap gate has the same process matrix as the first swap? Because I mean, I understand in your system, the heating effect can be very obvious. That might affect your swap gate comes later in the sequence compared to the swap gate comes earlier in the sequence.
Yes, indeed. Thank you for your question first. And yeah, I agree that if you have heating in your system, then indeed you might have a different swap for your initial and final swap gates. But in our case, we didn't really experience that first. And also, like, at least for shorter sequences, from the GST itself, you can already tell if you have different gates per attempts, because if your gate changes, depending on where it appears in your sequence, then it will suddenly show as having a very high non-Markovianity in your system in a sense. So I think that could also already tell you if you're suffering from heating or not. But in our case, we saw very low non-Markovianity for all of our gates. So I think that was okay, luckily, in a sense.
Yeah, okay. So my point is that I feel like the GST sequences are generally much shorter than this swap sequence you apply, which consists of like 400 gates. I remember up to 400 or something. But nevertheless, maybe I'll just move to the second question about the polytorting you did. Did you actually do a randomized compiling or just the polytorting, which gives random output?
We did randomized compiling.
Okay, so that's randomized compiling. Okay, that's my question. Yeah, I just want to.
But this, we didn't really do a measurement. This is a little bit more of after analysis we did with our process matrices.
Sorry, I don't quite understand what you are saying now.
So we simulated the polytoiling experiment using the process matrices we characterized from GST.
Yeah, but the polytolerant that you simulated, that's you simulated in the way of randomized compiling, right?
Yeah,
so
yeah,
the
yeah.
equivalent sequence. Yeah. Okay. Okay. Thanks. Yeah.
Yeah.
Were the single qubit gate fidelities, were they including the effect on the other qubit, or was that the kind of the sole fidelity of a single qubit?
Yeah, that's a very good question. In the numbers we report here, that's only considering the single qubit subspace for this case. So that already kind of gives you a pump, like a jump in the fidelity, because you kind of are able to ignore the other spin. But yeah, that's true.
Measure the fidelity for a single qubit gate, given that you measure the effect also on the other.
So using GST is a bit difficult because you have to have you have to fully characterize your process matrix, and then that already, in a sense, you have to send your other qubit out of its eigenstate to get the full information. So yeah, there's kind of a conflict there, I think. Yeah.
Hey, Jiwon, thanks. I had a question. I think somewhere in your presentation you mentioned that you're not suffering from the spam errors, since you sort of include the gates you do in the state preparation and measurement. Could you elaborate on that? Since I would say that, say, for example, when you want to prepare your electron, you do a spin pump, which is something different than the microwave RF gates that you do. How do you sort of separate out the spam errors then in this case?
Oh, so in GST, actually, those initial state also comes in a different kind of density matrix form. So that information is also there. The spam error is not regarding that, but just regarding the imperfection in your gates. In this case, what I was referring was your gate imperfection.
But do you mean like your GST also outputs what the spam errors are?
Yeah, what your readout is and what the initial state is, yes.
Have you benchmarked with any other like techniques? Or I don't know what Shao was saying about the easing, or like, can you use randomized benchmarking, or?
Yeah, so we did try randomized benchmarking on the system, and like for the electron gates, at least they were showing very similar numbers. Yeah.
Oh, and sorry, is the noise model that GST assumes well suited to nitrogen vacancies?
Sorry.
Like it assumes a certain model, right? Like a certain noise model, like non-Markovian noise. And is it well suited to your system?
In our case, I think it was, since we were characterizing a very well isolated two-spin system, and then there was nothing much happening like in the surroundings. In that sense, we were measuring very low non-Markovianity because we didn't really have anything. But yeah, if you have other spins in the system, then you might suffer from higher non-Markovianity, and then the reliability of the report itself kind of gets lower from what they say. Yeah.
When you show the unintended rotation thing, is it obvious directly from error generator, or because you also do many other things to discover this, right?
Yeah. So the unintended rotation, you mean?
Yeah, is it directly obvious from error generator?
Yeah, that's a very good question. So no is our answer, I think. So if you see you already have to know what you expect and then where it will appear in the error generator. And if it appears there, then you can know that that's happening. Like, it's kind of the other way around. If you just see the error generator, then you can't really pinpoint it directly with that. You do have to need some prior information of your system in that sense, I think.
Okay.
Yeah.
But then so it's not, you see, so that's not what exactly happened when you find the unintended rotation, right?
Yeah, so for us, we measured this rotation first, the rotation we saw in 8.3 microsecond, and then we saw in the error generator that there was a ZZ coupling between the two spins. So then using the two informations, we were able to kind of go to the better 7.304 microsecond.
But why it is ZZ?
Because that's originating from the coupling strings between the electron and the nitrogen. Or that was the mechanism of this nitrogen rotation, at least.
But why not is XI or IX? Why it is ZZ?
That's a very yeah, it could also be other things, but the one we pinpointed was the ZZ coupling there, yes.
Are there more questions? If not, let's thank the speaker again.